Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Velayat Khan. I'm an assistant professor at Comsets University, Islamabad work campus. The topics and the presentation slides uh, included in this lecture have been edited from the two sources given here. The topics that are included in a discussion during this lecture are buffering and demultiplexing, external fins of 8086 and 8088 microprocessor. So far we have, these are the two microprocessors, 8086 and 8088 microprocessors. In these figures, the external fin layout of the two microprocessors is given. In previous discussions where we had long detailed discussion about the internal architecture or the programming model of the 8086 microprocessor and other members of the Intel family of microprocessors. In the internal structure or in the programming model of the Intel microprocessors, we studied in detail and learned about the number of programmer visible registers and their sizes and their functions. We knew what are the purposes of each register, and in conclusion, those registers are used to store data and instructions when the microprocessor is executing programs. The operations and signals of addresses generated by those instructions are then externally connected with the external buses, control bus, data bus, and address bus through a number of pins. These pins are given in the dual inline packaging, where the microprocessor includes pins on both sides of it. For example, both of these microprocessors have 40 pins, and in each microprocessor 20 pins are organized on the left side and 20 pins are organized on the right side. But in both of these microprocessors, there is slight differences between the pins and their function. For example, 8086 is a 16-bit microprocessor, 8088 is a 16-bit microprocessor. That means that the internal registers in both of these microprocessors are 16-bit wide. But the data bus in 8088 is 8-bit, while in 8086 it is 16-bit. So 8086 can read 16-bit data at a time, while 8088 can read 8-bit data at a time. In both of these microprocessors, a number of pins are multiplexed. That means that they are used for multiple purposes. For example, the pins highlighted in 8088 microprocessor, these pins are used for address as well as for data. So as data bus is 8-bit wide and 8-bit data can be read by the 8088 microprocessor, so the address pins, the 8 address pins are multiplexed for data as well. So they are represented with AD0, AD1, AD2 until AD7. So these are 8-bit, which represent the 8-bit of data as well as the lower 8 bits of the 20-bit address generated by the 8088 microprocessor. Similarly, in 8086, it has a 16-bit data bus, so it has to send 60 or receive 16-bit data at the same time, and for that there are 16 pins of the address that are used for data as well. So these 16 bits are multiplexed for data as well as for address. So by multiplexing, we mean that these pins can be used for sending a memory or input and output address as well as sending or receiving data. So these multiplexed pins are represented with AD0 till AD15. So in this aspect, the difference between the two is that here address and data multiplexed pins are 8, here address and data multiplexed pins are 16. Apart from that, there is a pin 28. It is designated as IOM. This pin means that this indicates a value that would control the external circuitry to instruct them to whether access input and output devices or the memory. So IOM means that whether input and output devices are accessed this time or the memory is accessed. But in this labeling in 8088, IO comes first, while here memory comes first. So when a 0 is sent through this pin, memory is accessed. When a 0 is sent through this pin, IO input and output devices are accessed. So that is the difference between the two in this pin. Similarly, this is a status pin, and it is not multiplexed, where it sends some status signal, while here in 8086 microprocessor, the same pin is multiplexed with a status signal, as well as this has a bus high enable, and this bus high enable pin enables the high part of the bus when needed. For example, in 8086 microprocessor, it can access 16-bit data, as well as it can access 8-bit lower data, as well as it can access 16-bit upper byte. To enable the upper part of the bus or the bank, 8086 can be connected with two banks, each of 512 megabyte. So we will talk about this later on. So this bus high enable or bank high enable is used to enable the high bank of the memory. So this is the third difference between the two microprocessors in terms of the pin layout. 8086 or 8088 microprocessor is connected to an external clock generator to receive the timing signal or the clock signal. So this is 8086 or 8088 microprocessor, and these are some signals. I'm not talking about the timing. 8086 and 8088 microprocessor are receiving a clock signal from the external source. This is the block diagram of 8284A clock generator. So this clock generator has inputs where X1 and X2 are the two inputs to an internal crystal oscillator, and that internal crystal oscillator is connected through these two fins with an external crystal which generates a signal, and normally that is normally a 15 megahertz signal, and then this signal is then internally divided by a divisor or by a counter with 3 in with that would generate a clock signal of 5 megahertz, because then crystal oscillator generates frequency of 15 megahertz, and when this is divided by 3, we get a signal with frequency of 5 megahertz, and this is then given as an input to the either of the two microprocessors. Similarly, when this signal 15 megahertz is divided by 6, that is equivalent to dividing first by 3, and then there is another counter that divides it by 2. So this would give us at the end division by 6, so that would give us 2.5 megahertz, and this clock is normally connected with peripheral devices, so that means peripheral clock. So this is connected with peripheral devices, and then there is a reset output as well, and that is connected with the reset pin of the 8086 and 8088 microprocessor. There is a pin FC, that means whether a frequency external frequency can also be connected with this generator. So whether the input to this generator input signal is taken from a crystal here, which is connected here, or whether it is taken from an external frequency input. And in this case, as the input is taken from a crystal, externally connected crystal with these two inputs, this input FC is connected with a ground, and with this, if the input to this frequency generator is taken from an external frequency input, that external frequency input may be another 8284A clock generator, and in that case this clock synchronization input is connected to ground. This clock synchronization input is normally used in multi-processing environment when there are multiple 8284A clock generators are connected with each other. And here we have a reset input. There is a reset input button, hot button, push button, and also there is an RC circuit that generates the reset input. So in 8086 and 8088 microprocessor, the clock the clock signal is coming from an 8284 clock generator. Here is the detailed internal structure of the 8284A clock generator. So here are the two inputs which are connected with a crystal. They generate 15 megahertz of frequency, and then here we have a crystal oscillator, and the output of this crystal oscillator is directly connected through a buffer with an oscillator, and this oscillator may be given as an input to another 8284A clock generator in a multi-processing environment, in a multiprocessor environment where multiple clock generators are used. One is driven by the other, and then there is a frequency, external frequency and crystal selector. So here we have an input which is external frequency input. So the frequency input that is given to this generator is either a crystal or it is either an external frequency input. This external frequency input may be coming from the another clock generator. So whether the frequency input is from the crystal or whether it is an external frequency inputs. So this is chosen by this input. So for example, F is 0, F is 1, for example, then this one is connected with this, and this one becomes 0 here. So this there is an AND gate, and as this input is 0, so whatever we receive here is that will be ignored. So when F is 1, the external frequency input is chosen. When this input is 0, then the crystal input is taken, and this clock synchronization input is connected to 0 when this input is not used, when the external frequency input is not used, as we saw on the previous slide. Okay, so when the signal is received, this is divided by 3, and when this is divided by 3, this is passed through a buffer and connected with the clock output, and this clock is given as an input to the microprocessor that we saw on the previous slide. So for example, if we get 15 megahertz frequency here and this is divided by 3, we get 5 megahertz frequency here. While if the same frequency is divided by another counter here by 2, then we get peripheral clock frequency as the is 2.5 megahertz, which is connected to the peripheral devices. So this is a reset. This is also connected with the input, reset input of the 8086 or 8088 microprocessor, and this circuit generates a ready output which is also connected to the ready input of the 8086 and 8088 microprocessor. This is the clock that is in case of 15 megahertz of the crystal, the clock signal is 5 megahertz. This is connected to the clock signal of the 8086 and 8088 microprocessor, and this is the oscillator output which is connected to another 8284A clock generator in case of a multiprocessing environment. Demultiplexing and buffering is used before microprocessor 8086 and 8088 microprocessor is connected with external environment. So demultiplexing means that the address and data and address and status buses are multiplexed to reduce the device pin count. So these buses must be demultiplexed. They must be separated. Their functions must be separated to obtain the signals required for interfacing other circuits to the microprocessor. So we just saw in the beginning of this lecture that 8086 and 8088 microprocessors have a number of pins that are multiplexed with each other with different functionalities or for different functionalities. 8086 and 8088 microprocessor are generating 20-bit addresses, and they are generating 8 or 16-bit data as well. So are sending or receiving 16 or 8-bit data as well. So if we had 20-bit address pins and 16-bit data pins separately in 8086, let's say, and talk about 8086 microprocessor, then we would need additional 16-bit pins. But if they are multiplexed with data and pins and address pins are multiplexed with each other, if they are used for multiple purposes, then this reduces the number of pins on the microprocessor. However, this reduction of pins on the microprocessor is not free. Uh, they must be separated. Their functions must be separated. As when the address is sent through these pins, the address must be on the address bus for some certain amount of time to get stable, to get everything stable. But in the meantime, just after the address is sent, the same pins may be used for the sending data. So to relieve those pins for the from the address for the data, then they should be separated. Their function should be separated so that those pins should be ready for sending data immediately after the address is sent. And for that purpose, demultiplexing is used. So the address latch enable pin is play a significant role in demultiplexing address and data pins from each other. And also status fins and address fins are multiplexed. If you remember, the fin A16 till A19 are multiplexed with status signals. So status status and address signals must be separated from each other, and address and data signals must also be separated from each other. This is called demultiplexing, when their functions are separated. Even though the fins are the same, they are used for two different purposes. But once they are used for one purpose, immediately after that, the same pins can be used for a different purpose. While at the same time, to keep the external signals stable, they should be separated using demultiplexers or external latches or transceivers. So this is called demultiplexing. We will see some examples of 8086 and 8088 microprocessor when their multiplexed pins are demultiplexed. While buffering is used to increase the signals or the increase the number of devices to be connected with signals. Because the fan out of the microprocessor pins is limited, not many devices can be connected directly with them. Output signals which are not demultiplexed should be buffered in large systems so that multiple input and output devices may be connected with the external fins of the microprocessor. Here we have demultiplexing of the 8088 microprocessor. So here we have the 8088 microprocessor, and on one side we have the pins of the microprocessor which are either multiplexed or whether they are not multiplexed, but they are important to be connected to generate the address and data and control bus. So there are some control signals which are required to demultiplex multiplex buses. So if you remember, in 8088 microprocessor, the last four address fins A16 till A19 are multiplexed with status signal S3 till S6. So these signals these fins should be demultiplexed. Their functions should be demultiplexed. If we need to create 20-bit address bus, then we have to take these four bits from these four multiplexed fins, and the rest of these fins are not multiplexed, so we can connect them with direct with address bus, and we do not need to demultiplex them. While the lower 8-bit are multiplexed in 8088 microprocessor. Remember that in 8088 the data bus is 8-bit wide, so only 8-bit lower 8-bit of the address and data are multiplexed with each other. So 80 till 87, these fins are multiplexed for data and address. So these fins should also be demultiplexed. The data should be separated and the address should be separated. So we have some control signals IOM when whether input and input and output devices or memory is being accessed, read, write, and maximum mode or minimum mode. So this is connected with +5, that means logic 1. So a minimum mode is selected. So here we see the situation when 8088 is used in the minimum mode, and multiplexed fins, all of the multiplexed fins are multiplexed. So this is 373 a chip that when that is enabled, it just allows us the inputs provided here to the output. When this G is set to 1, this chip is enabled, and the same chip but with 8 inputs and 8 outputs is used here as well. So the output is connected to output enable is connected with ground, output enable is connected with ground, so it allows the output whenever the input is available, and the input is fast to the output when this G input is 1. This G input is the select input of these chips. These two chips are the same, just only this is a 4 input and 4 output pin. This is an input and 8 output pin. So whenever the address is being sent through these multiplexed fins, microprocessor will generate a 1 at this fin address latch enable. So this address latch enable will enable the latches here. So it is easy now to remember the function of this fin, because the function of this fin is address latch enable. So it enables the latches to separate the addresses. So these two latches would allow the addresses whatever available at these inputs, to be given as output whenever the address latch enable, and exactly that is the time when the microprocessor is sending the address on these multiplexed fins. So microprocessor puts 20-bit address and on these fins 80 till A19, and when that address is sent through these pins, the microprocessor will send a high signal on this address latch enable pin, and this will select these two chips, these latches, and these latches will allow the inputs which would be taken from these 8 lines and also from these 4 lines to be connected to the external buses. So the address bus will get 20-bit of its address. 8 would be directly taken from these 8 pins, while 8 would be taken from the 8 multiplexed pins, 4 will be taken from the 4 multiplexed pins, and 20-bit address will be generated, and this is connected to the 20-bit address bus. And just after the address is sent through these lines, after that the address latch enable is again 0, and whatever is provided after that were these pins, and these pins, they will not be passed on to the address bus. So for example, if later on, if the microprocessor intends to send data or receive data, the same pins would be available for use for data, and similarly the same pins would be available for use for status signals. So in this figure we can see that the 4 status address signals fins are demultiplexed, and the 8 address data fins are demultiplexed. The address is separated whenever the address is intended to be sent through these multiplexed fins. While here we can see that this is 8086 microprocessor, so the difference between the two is that here the 5 bits A16 till A19, and this bus bank high enable and status S7 are multiplexed. So we need to separate the bank high enable from the status S7, and also we need to separate the A16 till A19 from the status signal. So the same latch is used. This will just pass on the input to the output whenever the G input is 1, or whenever this latch is selected. And for the address and data demultiplexing, as in 8086 AD0 till AD15, these pins are multiplexed for data and address, because in the 8086 microprocessor the data bus is 16-bit wide. So to generate and to separate these 16-bit data from these 16-bit address, we need two latches, 8 to 8, 8 into 8 latches. So this latch will get 8-bit inputs and will release the 8-bit outputs as soon as the inputs are provided and when this chip is selected. And the same ALE input is connected, output is connected with the select input of the another latch, 373 latch. So this is again, it will pass on the bits available here to the output whenever the G input is 1. The output enable of all these latches are 0. So to enable the output whenever the input is available. So when the microprocessor intends to send address on these signals, and for that moment address latch enable, when the microprocessor needs to send address through these pins, multiplexed pins, address latch enable is set to 1 for a while, so that the address is put on the buses. So the address is put on this address bus, and these latches will keep these bits, the values of these bits stable for some time, so that the address, the 20-bit address is stable on the address bus, and this would not need these pins to maintain the value of that address for longer time, because the latches do exactly that for the address to get stable. While soon after the address is sent and passed on to the address bus through these latches, the address pins and the multiplexed pins here and here are now available for sending the status signal and also for sending the data bits, which is connected to the address bus. Okay, so sorry, which is connected to the data bus here. So 16-bit data bus. Okay, and the control signals are not multiplexed, so they are just directly connected with the control bus, and they do not need to be demultiplexed. So we have just multiplexed all of the multiplexed pin of 8086 in 8086 microprocessor, and on the previous slide we demultiplexed the pins of 8088 microprocessor. Buffering is needed because in microprocessor pins can only drive 10 devices when they are connected. But in a complex system, when multiple devices needs to be connected with the external pins of the microprocessor, then these pins should be buffered so that they would be able to connect more devices. So for buffering to buffer all those pins which are demultiplexed do not need to be buffered, because the latches the latches used here 373, these latches serve as the buffer as well. So they are demultiplexing the pins, multiplexed pins, as well as they are buffering the values or the bits available there as well. So they do not need to be buffered again, but the pins that are not multiplexed should be buffered, and for that other transceivers should be used. Unidirectional and bidirectional transceivers should be used, just like here. This is the fully multiplexed and fully buffered 8088 microprocessor. So if we remember, these four pins, address pins and status pins, and these 8 pins were multiplexed. So they were demultiplexed using this latch and this latch. So these pins do not need to be buffered. They can directly be now connected with multiple devices. The signals are also stable due to these latches. But the pins which are not multiplexed, for example, these control signal pins, they were not multiplexed, so they were not demultiplexed using the latches. Similarly, these pins in 8088 microprocessor were not multiplexed with data, so they were not demultiplexed. But these pins and here these pins must be buffered using 2LS74LS 244 transceivers. These are unidirectional transceivers. They are now buffered as well. They are unidirectional. They just provide output. Whenever the input is provided, they just pass on the inputs to the outputs. So they're nothing. They're not that much complicated circuit. They're just passing on the inputs to the outputs. So now these control signals and these address lines can be connected with many devices, external devices and buses. But here we have the data, and as the data is bidirectional, sometimes the microprocessor needs to send data and sometimes it needs to receive data. So for this, a different kind of transceiver called LS74LS245 transceiver. This 245 transceiver is a bidirectional transceiver. So it controls the direction of this bus because data can be sent to the external devices and the memory, and it can also be read from the external devices and the memory. So for that we need to control the direction as well. So this transceiver is controlling the direction of data as well as it is buffering these pin and these buses as well. Okay, so what this transceiver is doing, the data address enable pin is connected with the G input of this transceiver. So this is active low. So whenever a 0 is sent through this pin, this chip is selected. So whenever microprocessor needs to send data, it will keep address latch enable 0 at that time when the data is being sent. So it will block, it will disable this chip. So whatever is available here will not be passed on here because this is address bus and we are sending, the microprocessor is sending the data here. And whenever the microprocessor is sending data, so that means the direction is out of the microprocessor. So the microprocessor will put data here and will put 0 here so that this transceiver is enabled, and data transmit receive pin will set the direction of this transceiver. So as the data is being sent, so data transmit DT, that means a 1 is set here. So when DIR, which is the direction, when it receives 1, the direction is out of the microprocessor. So this transceiver is enabled by data address enable pin, and the direction is set to be going out from the microprocessor. And exactly at that time when the data is being sent, the address latch enable is 0. So this chip is disabled, this chip is disabled. So whatever is provided here, that data is sent to the data bus, and this transceiver is passing on the inputs here provided to the data bus here. And so this transceiver is doing two functions. It is buffering the data bus as well as it is controlling the direction of the data as well. And if we fully multiplexed the 8086 microprocessor, it is exactly the same situation, only the address pins are demultiplexed as well. And there are two chips, two bidirectional chips are used here because we have 16-bit data. So whenever the 16-bit data is provided here, the address latch enable is 0 so that it will disable these latches, so it will not pass on the data available on this data bus to the address, so it will just block these paths. And the data address enable pin will just select these transceivers, and the data transmit and receive will control the direction of the data here. So for example, if the data is being received, then DAN will be 0, so that these two chips are selected, and the data transmit receive pin is 0, so it will control the direction of both of these transceivers towards the microprocessor. So this is the diagram that represent 8086, which is fully buffered and fully demultiplexed. So 373, 373 and 373. These are demultiplexing the multiplexed pins, while 244 is a unidirectional buffer that buffers these control signals. And these two buffers, they are two bidirectional transceivers, so they are not only buffering the data bus here, but also they are controlling the direction of the data as well with these control signals. Thank you.